Okay, so um, only big reminders, I guess, is that that there is a reading. It should be relatively short and relatively high level. Introduction from Melanie Mitchell's book on complexity. And I've only signed up to page 22. So chapter 1 is just a few pages, kind of an introduction to complexity. And chapter 2 is an introduction to dynamics and chaos. And then after page 22, inside chapter 2, she goes off on a very popular example called the logistic map and how it gives rise to chaos. I'm going to talk about some different examples today that I think are a little more concise, but which is why I've had to sort of stop there. But for those who are interested in this content material, you can feel free to keep reading, but all perusal is going to ask you for is up through page 22. Again, that's for Thursday. And I'm getting assignments generated as quickly as I can, as I'm also coming up with the lectures. So as they trickle out slower, assignments might be combined, and I'll sort of adjust drop policies and things like that, so that you're not my delays in getting the assignments out will still give you plenty of opportunities to make choices on how you want to score points. One thing I know for sure, just due to the timing of it, the Unit E assessment will probably be combined with the midterm review assessment. So most of the questions in midterm review will be randomly sampled from previous assessments, but they'll have a few new questions about E. And then the benefit to that is you'll be able to take that one as many times as you want, and it'll take the highest score. So it'll be slightly more points, which allows you to get points for Unit E and the midterm review, and you get to take it as many times as you want. So that's sort of one example of pooling these things together. So we're going as quickly as I can, but otherwise that's about it. So any questions? Yeah. I'm probably going to, because C and D are blending together, and what I may do is make the assignment either, what I'll probably do is bring both assignments out at the same time or roughly the same time, and then they'll have similar due dates. And then that way you'll have the opportunity to do both if you really want to, or you could count one towards your drop or something like that. Okay, any other questions? Thanks for the muddiest point submissions were great. I forgot to send out a reminder to poke those who didn't submit them on Sunday. So on Monday, nearly everybody had submitted them. So that was great. And reading through there was interesting to see your thoughts. And hopefully some of the questions that came up there will be answered here as well. So, you know, from last time we were talking about how, you know, we have system dynamics in different, you know, sociological systems. And I've been using this fishery example as one case of that, but this could apply to other sorts of examples too. So, you know, I'm not going to go through all the fishery example again, but just putting it here as a cartoon reminder, you know, this is, you know, with the net regeneration rate and the harvest rate. You know, this is a simple, you know, a sample, not simple necessarily, but a sample dynamical system where if we knew all the math behind it, if we modeled what the regeneration rate was mathematically, we knew what the harvest rate was, we could try to make some predictions about where the system would be if after you disturbed it, how long, you know, it would come back. And so we can do that mathematically. That's one of the things you can do, or you can kind of get a sense for what's going on. And you can say, well, we know that whenever the harvest rate is higher than the net regeneration curve, then the fish population declines. And that's where these arrows came from. And whenever the net regeneration rate is higher than the harvest rate, the fish population climbs to the right. And that's where the arrows came from. And then that sort of gives us a hint that there's some sort of stable fish population for each harvest rate that's sustainable, and there's some extinction equilibrium for every harvest rate, and well, it's just extinction everywhere, that is not sustainable, it's extinction. And there's some threshold that separates those two things together. And that gives us this idea of these two stability regimes, where we have the regime of stability of extinction, and we have the regime of stability of the sustainable equilibrium. And if you manage to start the system with the fish in the blue regime, then over time it'll go to the blue dot. If you start the system where the fish population is lower than the threshold, then it'll go to the red dot, at least so long as the harvest rate is held at that level. And so, that starts to give us an idea that these systems do have some structure. And so to give us a little more intuition, we translated that into a physical model, or the ball-and-basin model, where we, instead of plotting these quantitative things, we plot something a little bit more abstract, where we still consider fish population. So in this case, fish population. But in general, this is an endogenous variable, a variable that's changing fast. It's a variable that's changing in our observation period. We can still plot the same thing, but on the x-axis, that endogenous variable. But we replace the specific dynamics with what they refer to as a potential function, but it's basically just a bunch of hills, a bunch of basins whose sort of steepnesses would allow a ball, if you started it anywhere, if you think of this as a coordinate along latitude and longitude, if you think of this as like latitude or something like that, or maybe it's a longitude, and then these are altitudes. And then if you started the ball at any particular longitude and whatever altitude you're forced to sit on, then you could watch its longitudinal trajectory, its trajectory across all these different coordinates, and see where it settles out. And so we came up with, well, what would such a model look like? Well, that I've got sort of a valley here, a hill that is separating the two of them. So something along the lines of maybe this. And so that way, if you happen to be, so this is our blue equilibrium, and this is our red equilibrium down here. And so if you happen to be, start at any particular position, we would expect the ball to roll downhill and eventually come and settle out at the bottom of the basin. And likewise, if it was over here, wherever you start it, it'll end up at the bottom of this basin. And so you get this similar sort of interpretation, where now these stability regimes correspond basically to the extent of these little cups, these two cups that are in this physical space. So I could, similarly draw a little regime where I'd say, well, this regime here, that is our extinction regime. So if your fish population's here or anywhere below, it'll roll down into that valley. And here, this is our sustainable regime, where if your fish population starts anywhere in this valley, it'll roll down to the bottom here. And so that gives us a little bit more intuition for us to think about these things. And the way we translate that, that intuition, we'd say, well, that way we can make predictions about how things will behave over time based on where they start. So predictions about behavior over time, which I'll abbreviate BOT, behavior over time, kind of a standard abbreviation in this field. So in that case, now I can translate these plots into a plot with time on the axis. And now the fish population is going to be on the y-axis. And so basically we've got, if I call this stable point P star, that's the, and then, this one down here is 0. So I'll write that down here, P star and 0. Then we can map those onto the vertical axis where we might have our 0 extinction, some point P star. I'll draw a little dotted line to remind me where P star is. And there's some threshold in between them. And maybe our carrying capacity up here, just to remind us we can't go any higher than that. And what our intuition from this model is, we plot it over behaviors over time, this sort of says that if we were to start anywhere, and maybe I'll draw that highlight again, but now vertically, if we start anywhere in this region, we'll end up landing on P star. If we end up start anywhere in this region, we'll end up landing at 0. So if I were to consider many different, what I'm going to call initial conditions. So if I start the lake with this many fish, if I start the lake with this many fish, I can say, how does the fish population change over time? And what our intuition is from this is that we get this kind of picture where if I start up here, then it's going to decline smoothly and eventually land at P star. I start a little closer to P star, same type of thing. If I start far, but still in the blue region, but far from P star, it might look kind of S-shaped. So maybe it'll rise up and then level off. And as I get closer, it still looks kind of S-shaped, but you get less of that kind of S curve. And so everything kind of collapses onto P star. But if I were to start below that threshold, then if I start really close to the threshold, it just goes to 0 fast. If I start a little bit above it, a little bit above it, and so on. So all of these initial conditions just, over time, go to 0 fish. All of these initial conditions over time go to P star fish. And so that's what we mean by saying that these are two stable states or alternative stable states of the fish system, and why we'll also sometimes call them attractors. Maybe I'll write that in a different color. And the extinction is an extractor, and this sustainable is an attractor. And I hope it's clear. I might clean up this blue line that I drew up here, just because it doesn't look like it's landing in the right spot. So I'm just going to redraw that so it lands on P star. So here. Something like that. All right, that's kind of close enough. So we can see that regardless of like wherever the fish are to begin with, they're all attracted to this. And here they're all attracted to this. And I say initial condition, but really I mean like anytime you disturb the fish. So it's like if you dump a bunch of more fish into the fishery, you've just changed the kind of initial condition. And then you wait to see how quickly that disturbance is rejected. So how quickly do they get back to stability? And we can kind of use this picture to give us an intuition about this. But ultimately, this is sort of what we're trying to predict. So that's kind of the pathway we've gone through so far. Are there questions about this? Yeah. Mm-hmm. Yep. Oh, well, okay. Well, so that's a great question. So if it starts up here, can it kind of go up and then over? And I would say that for one thing, yes, you can as a simpler case, you can start somewhere and then oscillate. until you eventually settle. And that would look like, let's say started over, let's say start down here. You can rise quickly and then in some systems oscillate and then settle down. But there are other systems where you can get sort of these quasi-stable states where things kind of speed up and slow down, but end up somewhere else. But yeah, I mean, that is part of the gift that we get from this intuition here, is that this height is finite. And so in theory, I mean, I just arbitrarily drew this, so maybe this wouldn't be the perfect one for the fish model, but we could come up with systems that that would build up enough momentum that this basin, even if they started in the basin, if they pick up enough sort of, I want to say kinetic energy, that they can actually escape this basin and end up somewhere else. So it is definitely possible to construct systems like that. And actually, I guess I would say, you know, we go the other way. I can actually go and take this, like, this is a physical landscape. And that is something that could happen. You could put a ball higher than this point, drop, and if there's very little friction, it could go right over this thing. I could write the differential equation. I could go to physics class, you know, calculus-based physics, and write the differential equations governing this system and draw one of these things for it. So basically, the ball-in-basin model is like just it's a model system, but it is a system in itself. And so absolutely, if it can happen here, there's math that can describe it. And once you've got it in the math, then you can actually start seeing that, you know, actually this math looks really similar to the fisheries math. And then you could come up with a fishery situation where that might be the case there. Or you could say, actually, in a fishery, that would never happen because the math just doesn't match. Does that answer? So any other questions about this process that we've sort of built up until now? We kind of, you know, our goal in this class is to not have to worry so much about these, you know, very concrete, specific systems where we actually have to model out all of that. But we want to build up the intuition that many systems can be viewed as some sort of ball-in-basin, and there's some exogenous variable like harvest rate that as you move it around, it moves the basins around. And if we can have an idea of how, well, if you move the basins around, it changes the behavior over time, then that gives us a feeling, an intuition for the, at least qualitatively, whether we're losing resilience or gaining resilience in a system. So that's where we're just sort of building up resilience thinking, which is really more about these two boxes over here. But I only introduced this one to show you that there is a concrete system that actually generates this picture. I didn't just make this cartoon up. Okay. Okay, good. So, and I guess the only other sort of term that I've been talking about here are initial conditions. So, you know, these here, I'll just mention, you know, I might use that term a lot, initial condition. And I don't necessarily mean, you know, when time began, but I mean after some disturbance to the system, how long, you know, what is the response to that disturbance? And that relates to the, you know, this, the amount of time it takes for things to settle out is the sort of, and they called it the recovery time in those articles from last week. So some systems will very quickly hit their attractor, other systems take a very long time to hit their attractor. But every stability regime is associated with an attractor, and initial conditions that start in that regime are attracted to that attractor. That's the idea. Okay, so I mean, with this, we can see there's a possibility of regime change. So we can have regime change or regime shift. And there are different ways we can have regime shifts. So we can just, you know, artificially dump fish into a fishery. And we know that as we're driving fish into the fishery, we're moving this ball around potentially to go over a threshold into another basin. Similarly, it's like if you have a glass of wine, if you dump a bunch of wine into the glass, eventually the wine will go over the side of the glass. And that's because if the wine in the glass is sort of the endogenous variable, or rather maybe the wine on the table is the endogenous variable, then you've forced things to have no wine on the table into the point that has wine on the table. So that's what we refer to as an endogenous regime shift. So I'm going to mention this. So two types of regime shifts. And they're just endogenous and exogenous. So we have endogenous regime shifts. And these are the ones that you don't change the system at all. You just, you happen to take a variable and you disturb it so much that it finds itself in another basin. And this relates really well to a local resilience versus global resilience. And so I can draw a ball-in-basin. So imagine this is some endogenous variable, like fish population. And I'm going to draw it in two different basins. For comparison. So up in this top basin, I'm going to say, well, what if I have this basin that has these two kind of this sort of W-shaped characteristic here. So these two deep and steep wells versus something that maybe is really shallow. And so we can see that in this top one, there's a very strong recovery force. And so if you started in this basin, very quickly, you would end up at the bottom. And most of the time, you would be found in a small neighborhood of each basin. Because if you did have any perturbations, there would be a strong restoring force that would knock them back down so that you would get very little variation around these two basins. You have to be in this basin or in the other basin. You only really see things in those two points of view there. But that amount of stability typically means that you have this knife edge threshold in between, which means that if you do happen to have enough energy to push this fish population or whatever it is over that threshold, then it will snap into another basin. And that's like the local resilience example from the paper last week. So this is like has a lot of local resilience, where that's like the plot over time, where you've got sort of in one stability regime, and then suddenly it snaps and goes into another stability regime. So there's this regime shift that's sort of catastrophic. It completely moves to a different regime. And that usually happens when, and I'll say this is the endogenous variable. This is the behavior over time. And that happens when you just perturb, when a significantly large disturbance of the endogenous variable causes it to snap, versus the case down here where this, and so I guess I should say, maybe I'll also emphasize that these are strong restoring forces. But if you have one of these ball-and-basin models that looks like this, you have very weak restoring forces. And so the idea here is that if you happen to be just perturbed away from the equilibrium, it would take a longer time to come back to that equilibrium. And that would mean that you would observe this system in a wider range of the endogenous variables. So you would, rather than seeing it pretty much just at the bottoms of these things, you might see it in a wide range here. And so we refer to this as not having local resilience, because if you disturb it just a little bit, then you immediately see those disturbances and they stick around for a long time because it doesn't have like a lot of force to pull it back towards the center here. But you do have global resilience in that you don't tend to have these large regime shifts that correspond to this knife edge threshold in between here. So that's like kind of the ball-in-basin version of what that paper referred to as global resilience, where you've got your behavior over time. And I could say time, or I could say here, this, I think in the paper they used a stress. And so they stressed the system. They added more and more of it, the endogenous variable, until it snapped into the other region. And so here, if I were to talk about, time or a stress, if I added more and more stress with time, then I might get a slight change in my variable, but it doesn't make the giant leaps. And so we have gradual change. No regime shift. All right, so this is what I mean by endogenous regime shift. The system doesn't change, but you move the endogenous variable over a threshold, and it goes from being clear water to murky water. It goes from being a sustainable fish population to being extinct. And that doesn't happen because the system changed. It just happens because something moved the endogenous variable from one stability regime into another. It's not an exogenous effect. It's something that internal to the system. There was a small sort of predictable disturbance that gradually moved the system over one of these thresholds. So that's one type of regime shift. The system doesn't change, but the variable moves across a threshold. Any questions about that? That's like the only way the wine spills is if you put too much wine in the glass. That would be an example of an endogenous regime shift, because you've actually, if the level of wine in the glass is an endogenous variable, you've moved the endogenous variable gradually until it moved over the glass. Okay. So that's the one. So any questions about that, endogenous and versus the next one, which is the one that people are more excited about? So the other type of regime shift we have is an exogenous regime shift. And this is sometimes referred to as tipping. Okay, so in an exogenous regime shift, there's sort of two different types of exogenous regime shifts. If it were up to me, I'd only talk about one of them, but depending on who you talk to, some people refer to this first one as an exogenous. So the first one that I want to mention before I talk about the really exciting one here is a very large and unpredictable change to your endogenous variable. And so this is why I have a difficulty calling this tipping, but a lot of people do, because they view it as qualitatively different than what I just talked about on the previous page. So a very large, unpredictable change to an endogenous variable. And what do I mean by that? Like, for example, you might have an earthquake, or maybe some sort of solar flare, something that is so unpredictable that it's going to shock the system, but it's going to be a large shock that we will not be able, like we're not going to expect. It's like in the wine glass example. If in theory, there is a probability that all the wine in the wine glass will spontaneously jump out of the wine glass. It can happen. There is a physical reality in physics that there is some probability that all of those molecules of wine will just jump out of the glass by themselves without you jiggling it or anything like that. But it's only going to happen once in every like million years. If that happens, it's so rare that we don't usually think of them as endogenous regime shifts. We refer to that as tipping, as an exogenous regime shift, as a black swan, is something that is so rare that it's going to be catastrophic when it happens. But the best we can do is just put a time on when we think it's going to happen. So, this could also be very large floods or very long droughts. And so, that's why you hear like in a very in floods, you hear them like, oh, that was a 1 in 500 year flood. What they're saying there is we didn't change our flood infrastructure at all. And so don't blame us for not for screwing up the infrastructure. We just got hit by an extremely rare event that that was so catastrophic, it was almost as if we just totally broke down our infrastructure. And so that's why people draw a line between this. Like, there can be like, oh, we had a slightly larger storm than usual. That's an endogenous. That's like the floodwaters got a little higher than they normally are. Well, that might generate an endogenous regime shift where you happen to get, flooding into the city, and now the city's got water in it. But an exogenous regime shift is like the city's gone, because the flood was just way bigger than we could have ever possibly predicted. And that's something that is so much greater than that it falls under this category of tipping, is this special term for this. Now, tipping gets its name from the other type of exogenous regime shift that is what I usually kind of focus on. And that is when you actually change an exogenous variable to a point where you reach what's called a bifurcation, where the number of stability regimes changes. So that's the other thing, is that we can have a change in the number or type of stability regimes due to an exogenous variable I'll say due to a change in an exogenous variable. And this is known also, this particular type of regime shift happens at what's called a bifurcation point. And this particular type of regime shift is called a bifurcation. And I'll show you this graphically here, but the example would be like when harvest rate goes over the maximum net regeneration rate. At that point, this is what we define as overfishing. At that point, when you harvest more than the fish could possibly reproduce, there is no chance of a stable equilibrium. That stable regime disappears. The only regime that's left over is the extinction regime. That instant where the harvest rate reaches the max net regeneration rate, that's what's called a bifurcation point. The bifurcation was the disappearance of the sustainable regime. Okay, so I'll show a graphical example of that, but any questions, preliminary questions right now about this? Okay. This would be in the wine glass case. If you started to tilt the wine glass, the wine stays in the wine glass until the wine glass falls over. And that's where this gets its name. This is sort of the classical example. This is what we refer to as a classical tipping point. It's the angle of that wine glass where it falls over and spills all the wine. So you know, it'd be one thing if you were shaking the wine glass, the wine flew out of the wine, or the wine flew out of the wine glass just because you were jiggling it. That's one thing. But if you actually tilt a table to the point where the wine glass is fine, and the wine glass tips over, at that point on its side, even if you put the table back, the wine glass doesn't get the wine back in it. The wine glass doesn't right itself back over. That's where it gets the name tipping point, is that it's a point where the exogenous variable is the slowly changing angle of the table. And you reach a point in that exogenous variable where the system changes and you go from upright wine glass to wine glass on its side. It's like a totally different system. Just like the fishery goes from fishery with a sustainable equilibrium to fishery without a sustainable equilibrium, because your harvest rate hits that angle and it falls over. It's like the fishery falls over. So that's where we get the name tipping point. And so we have a way to graphically represent these things in resilience, and that's with something called a bifurcation diagram. And this is just a way to conveniently convey how large changes in an exogenous variable change the stability regime of an endogenous variable. So it takes like basically a bunch of those ball-and-basin models and stacks them next to each other. So the example here is on my x-axis, I'm going to put an exogenous variable like harvest rate. So just as a reminder, these are slow variables or control variables. They are things that we as an outsider control or set, and we assume that they change much slower than the rest of the system. And that's why they're not connected. They don't, on our causal loop diagram, they don't have any inflows coming into them. They only have outflows. And then on the x-axis, we do values of our endogenous variable, like fish population, but we're only going to plot the stable values. And so we're going to plot the long-term steady state values of the endogenous variable. So I'm going to put that here. The long-term or steady state values. So what do I mean by that? Well, if I think about it, if I'm harvesting, let's say I harvest at rate 0. If I'm harvesting at rate 0 and then extinction is 0 and my carrying capacity is up here at K, Now, if I'm harvesting at rate 0, so I don't harvest at all, does anybody remember what happens to the fishery? Like over time, what's going to happen to a fishery if you don't harvest it at all, the fish population? It'll go up all the way to the carrying capacity, right? So it just rises to the carrying capacity. So that's going to mean that we have an extinction equilibrium, but it's not stable. So I'm going to draw a little circle around it. The stable equilibrium is just the carrying capacity. Now, as we increase the harvest rate, then the fish population's stable equilibrium starts to decline. And it declines kind of like this. So it reaches some midpoint here. And so all of these points here that I just drew are the stable. Those are the stable equilibria, the stable, sustainable equilibria for all of these harvest rates. So for this harvest rate, there's one, if you happen to start with a fishery with enough fish in it, it'll go to that one. Now, remember, there's a threshold that represents whether things will go to the sustainable or go to the extinction. And we draw that unstable threshold as a dashed line that for this system happens to look like a mirror. And then the other stable equilibrium is the extinction equilibrium. So just to make that clear here, here's solid lines are stable equilibria or stable states, and dashed lines are unstable, or we could view them as thresholds. And so here in one plot, I can see that there is this point, which is the harvest rate at the maximum sustainable yield. And this right here is a bifurcation point. Because on the left of it, you've got two stability regimes. You've got an extinction regime and a sustainable regime. But on the right of it, as Harry Styles might say, things just aren't, I guess, as it was. There only is one regime, and that's the extinction regime. So you move smoothly at higher and higher harvest rates, and everything's fine. Everything's fine. Things are staying sustainable. The fish stock is declining, but it's not declining to 0, and we're getting more and more harvest out. Everything seems totally fine. Then you cross this bifurcation point, the stability regime you were counting on disappears. It goes away, and the only thing you have left is the extinction regime, and that's overfishing. So you've got overfishing to the right, and you've got sustainable fishing to the left. And so that's a reason why we call this a tipping point more generally, because when you cross this bifurcation point, you didn't actually like disturb the fish any, really. I mean, you increased your harvest rate a little bit, but you didn't shock the system with more fish. But it's just like that with that wine glass. You're like, well, if I tilt it a little bit, the wine glass stays up. I tilt it a little bit more, the wine glass stays up. Everything's fine. And then suddenly, it's almost like spontaneously the wine jumps out of the glass once you tip it too far and it falls over. And that's what happens here too. You didn't actually pull anything across the threshold. So there wasn't any endogenous regime shift. You just got rid of the regime entirely and the system moved to the new one. And so that's So if I wanted to highlight these things, so this is me adding my sort of flair to it. This is a typical bifurcation diagram, just solid lines and dashed lines. But if we wanted to annotate this a little bit, then basically you could say this whole region here and up here. I guess I could color that all in if I wanted to. That's like all of the stability regimes for the sustainable equilibrium. And then everything else is the stability regime for the extinction equilibrium. Again, this is just me adding things for illustration, not a standard way to do it. But that kind of shows you that if I'm just going to flip back for a second, if I look back at this diagram, you can see the red highlight and the blue highlight. Well, I've just taken that red highlight and the blue highlight, and that's like a cross section of one of these. Like for this harvest rate, we've got blue highlight on top and red highlight on the bottom. So for every harvest rate, I'm just stacking those initial conditions and their regimes up. And eventually I hit a harvest rate where there's only one regime, and that's over here. And so that's what's summarized in a bifurcation diagram. So every time you see a change in the number of regimes or the stability, so if a dashed line becomes a dotted line, if a dashed line becomes a solid line, if a solid line becomes a dashed line. So if the number of the regimes or the stability of any of the equilibria change, that is what's referred to as a bifurcation point. And bifurcation points are the sort of classical version of a tipping point. So questions about that? There are a bunch of different types of bifurcations. It's outside of the scope of this class to talk about them. This particular type of bifurcation is what's called a fold bifurcation because it kind of looks like a fold. And when you have two fold bifurcations like this one and technically this one, then you get something called hysteresis. And a hysteresis loop is when you start, like, let's say you started here. If you started at this point, well, yeah, let's see how many people are following here. If this is my initial condition, this is where my fish are. So what I'm saying here is I'm at this harvest rate down here, and I'm at this fish population here. So if I start at that point right there, that harvest rate, that fish population, where will my fish population go over time? Yeah, increase. Where? To the solid line, absolutely, great, perfect. Does everybody see that? That if I start in the middle and I fix my harvest rate, then this is exogenous space, so it doesn't move in time, it's slow. This is endogenous, so we're saying that we move upwards. So anything in this blue region moves to the blue line. If you started up here, it moved down to the blue line. So we start here, we move up, and we hit there. Any questions about that? All right, so then you get overzealous, right? You're like, this is great. I would like to fish more. So you fish, you move to a new harvest rate here. It's like a new initial condition. Where now that I'm at this new harvest rate, where is the fish population going to go? Down, right? I see a lot of fingers down. That's great. When I ask these questions, especially if I'm like holding this pencil here and can't really point or whatever. Yeah, if there's a way to answer me, like, and if you want to keep it close to your chest so only I can see, that's totally fine. And I'll like look for that. So yeah, so down it goes and it'll go here. Same logic as before. You're like, oh great, this is sustainable. Everything's happy. I've been fishing like this for years. I would like some more fish. So I moved to a new harvest rate out here. So now I'm at a new harvest rate. Now, and I guess I should make an X here to match my conventions, like a new initial condition. Now, where does the fish population go? Down, right? So it keeps going down towards extinction. And then you start realizing, I screwed up. There's something wrong here. Things, there are indicators that the fish population is collapsing. So I am going to go and before it hits extinction, I'm going to do the responsible thing and move to a harvest rate that previously worked for me. So I moved to this harvest rate, which used to be sustainable. But what happens? What happens to the fish population when I'm at this level here? Does it go down or up? How many people say it goes up? How many people say it goes down? Right, it keeps going down because I'm in the red regime now. Even if I'm at a harvest rate that once was sustainable, at this new fish population, it's not sustainable. So now I realize, shoot, I have to basically back out almost all of my boats and basically almost stop harvesting just to get back into the blue regime. And then I gotta wait for the recovery process to get back up to the stable equilibrium, and then I can start fishing again. So everybody follow that process I went through here, where I started at that big X in the middle, and there was one threshold that moved me into the extinction regime, and a different threshold that moved me back into the stable regime. And it's that difference in thresholds there is what's called a hysteresis loop, or hysteresis. So when you have, yes, I could probably write it here. When you have two fold bifurcations, you often get something called hysteresis, which is history dependence. So you get two tipping points effectively, and that's like one for one for shifting in one direction, and then another for the reverse shift. And this is a scary situation for that example that I just gave there, because as long as you stay in this, under here, you've got a lot of control. If things, you can back off, you can go forward, but so you don't have to worry about like major consequences to a little bit more fishing. You cross that point, you cross that maximum sustainable yield. Now you have to really pay major consequences, because the only way you can get back into the blue is by basically shutting down all of your fishing and waiting for things to come back to normal, and then you can start harvesting again. And that's what's so scary about these hysteresis effects here. Now, there are some systems where the tipping points are irreversible, like the wine glass. Once the wine glass tips over, there ain't no way you're getting that wine back in the glass. You can reset the table. So I can start the table out, the wine glass up, tilt, 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 wine glass tips over, wine spills. So then I tilt it back up this way. Well, the wine glass doesn't stand back up. So I think, okay, shoot, I need to go back way the other way. Finally, the wine glass maybe pops back up, but then once it's popped back up, it's still empty. It's an irreversible tipping point. And that's what people worry about. Things like, the ice, so the amount of ice on the planet, if it gets a little warmer, you melt all that ice, you might think, well, I'll just cool it down to the point where the ice was happy. Well, that's not going to cause the ice to refreeze. And even if you cool it down, the earth down to the point where you get the ice to refreeze, which probably isn't a great way to live, the ice won't necessarily freeze in the same place. So there are these systems, especially ecological systems, that have these tipping points which are irreversible. Once they're tipped, there's no way to get things back. All right, so any questions about that? And I want to make sure it's clear. A lot of people, like especially in the media or whatever, use the phrase tipping point to mean an endogenous tipping point. They're like, well, once we get a critical mass of people signed up for a particular event, then something will happen or whatever. But that's sort of like, moving from one stability regime to another. A true tipping point, in the sense that, how it was came up with, is a a change in a slow variable that causes the number of stability regimes to change. It's not a movement from one regime to another where the regimes are all the same. It is a movement, what is a movement from one regime to another, but it's a movement caused by a regime disappearing or a new regime appearing. So it's a change in the number or quality of the regimes. That's what a tipping point is. So questions about that? Okay. Okay, great. All right, so that brings us to what the whole point of those papers last week were about was, if these tipping points are so damn scary, then how do we detect that we're near one? Like here, everything was fine. Harvest rate, a little more, a little more, a little more, a little more. How do we detect? Like we probably don't know the net regeneration rate of a fishery perfectly. We might have a general idea, but we don't know it, perfectly. We also probably don't know how much fish are left in the fishery. It's really hard to know how much fish are in a fishery just by, you can't, like, it's not like they're tagged and you can like look down to them with a satellite or something like that. They're being born and dying and they're, it's just hard to tell. So the question is, you'd have to say, well, how do I know that I'm at a harvest rate near this critical point? Or, I'm at a harvest rate way back here. And that's where those papers last week came into play with critical slowing down, is that as a not meant to be perfect, it's meant to be a diagnostic tool to help you figure that out. And it uses these ball-in-basin models to sort of give intuition for this process here. And the basic idea is sort of one we've kind of already covered, is that if we consider two ball-in-basin models, so this is going to be our endogenous variable, so like our fish population. And this is our height, because it's a ball-in-basin model. Then the idea here is when we're far from the tipping point, then we might have two regimes, but there's going to be a strong peak in between them and a strong restoring force. And so the idea here is that I might have one regime that's over here, and then another regime over here. And so it might be that at the tipping point, this blue regime disappears. But if I'm far from the tipping point, the two regimes are there. And if I'm, imagine myself in this blue regime here, then I'm going to get very little variation in the actual values that I observe in my system. So little, so let's see, small observable variation in the endogenous variable. And on top of that, there is a fast response to disturbance. So if you happen to notice that a storm kills a bunch of fish, or you dump a bunch of fish in or something like that, if you do have some way to estimate the fish population, then it very quickly comes back to the old fish population. So so that's this is in the far case. And that's because this regime is very steep. But if I instead imagine myself very close to the tipping point, well, then in that case, I still have got maybe one regime over here, but there's not that much of an area for the other regime. So at this point here, this is much shallower. And because it's shallower, then we see large variations in the observable endogenous variable. And we see a slow response to disturbance. And that's where we get the name critical slowing down. So the idea here is that like our harvest rate has gotten so close to the maximum sustainable yield that we still have a sustainable equilibrium, but it's pretty slow in coming back after you disturb it. And that tells us that if we increase our harvest rate a little bit more, we're going to eventually, we're going to be pretty close to just rounding off that stability regime, giving us just one left over. So this steep regime becomes less and less steep and becomes shallower. Now, this doesn't always work, but in many systems, their underlying dynamics are described by potential functions that have these shapes. And as you move exogenous variables around, then you go from steep potential wells, steep basins, to shallow basins. And all of our insight from what happens with a physical ball rolling around steep basins and shallow basins translates to what would happen to a fish population as you perturbed it, or the murkiness of a lake. Like, so this might be easier to think of as this is a murky lake and a clear lake. And so here the lake is always clear, even after a rainstorm. It just very quickly clears up. But over here, you happen to notice that, like, remember last year when it rained, it cleared up like in a day. Well, this year I noticed after it rained, it took like a week to clear up. That might indicate that there's some slow exogenous variable, like the phosphorus in the soil, that that has moved to a state that's very close to tipping. And if this system tips over, it's going to be murky all the time. All right, so questions about that, the critical slowing down. And they mentioned in there that there's this recovery time. And that's what they refer to here, is this, it's the, how long it takes to respond to a disturbance. So if the recovery time increases, you might be close to a tipping point. Now, I only mentioned it briefly to say, so, you know, I gave you one paper which gave kind of a theoretical justification for this, another paper which actually did this in a lake and measured recovery time, but they had to measure, like, you know, they had to measure a lot of variables, you know, all the time for like 3 years straight. It's really hard to catch these changes in recovery time. And that's why I gave you that third paper. And it showed that there's also in some systems, there is a spatial analog to that called the recovery length. And it works in homogeneous systems, like systems that are either one species or another. If you can disturb that system, like around its periphery, so that you have, you go to that alternative state just in that one small area, you can see how far into the system does it take for the system to stop mixing with that disturbed state, like, you know, a type of vegetation. So you could put, you know, all shrubs and all trees. And so you can see, well, you know, if these are competing, these shrubs and these trees, but whatever one's dominant is the one that ends up taking over, how much of a transition period do we have between the all shrubs and the trees, the mixture period? If it's short, then that means our tree system is in this state over here. It's got a strong recovery force. If it's long, so there's a huge distance of mixed shrubs and trees, then that means it's probably here, where the tree system doesn't have the ability to sort of keep a hold. So in that case, you can take one snapshot and know you're probably closer to tipping. But that's like a very special case where things are spatially arranged that way. So, so really the real hope for critical slowing down is usually measuring recovery time, which is usually very difficult to do because it requires you watching a system kind of continuously for long periods of time. All right, questions about that? Okay, this is good. This is where I wanted us to be right around this time. And then so for the last couple of minutes of today and moving into a response to the reading for Thursday. The things that I've shown you so far are systems that are pretty predictable, so predictable that we can use these ball-and-basin models to understand them. But there are systems out there that are uglier than these systems, that are even harder to think about, and they emit certain phenomena that that we need to know about, so we can recognize it and figure out what to sort of do about it. And so, you know, one of these cases is, let's consider a delay. If there's systems with delay, it's very difficult to think about them in terms of a ball-and-basin model. So imagine a ball-and-basin model. And I'm just going to draw one basin like this. Nothing special. And then I'm going to put some system in here at some point. I'll call these points A, B, and C. And so a system maybe starts up here at A, and it maybe rolls downhill to B. Now, put a circle there. Now, in most systems that don't have delay, when the system is sitting up here at A, it feels a strong force to move downhill, but then that force goes away when it hits this stable point down here. And it might move past it and come back, but it generally kind of slows down and settles down right here. Now, you can imagine kind of a bizarro world where the forces that you feel are actually the forces that were put upon you 3 minutes ago or 3 seconds ago. So you can imagine that the steep forces that are put onto A don't actually get felt by A until it's at B. And so that's kind of what happens with delay, is that delay says that the forces at B come from position A. And so with that there, then again, it just wrecks our intuition, because what would happen here is that now, because B is now feeling the downslope from A, it's going to roll back up to C. But then once it hits C, then it's like the forces at C come from position at B. Maybe I'll draw a line and be here. So that would mean that once it gets up to C, it's going to then feel like, all of the slope kind of go away, and it's going to slow down up at C. And then eventually it'll come back down. And what you'll get is this ball like acting like a pendulum, just rocking back and forth, because it's always chasing its own tail. And so that right there is why, these sorts of systems, so systems with delay lead often to oscillations. where if I were to draw the behavior over time, I could draw my A, B, and C. And there might be some transients, but the steady state here may end up being persistent oscillations going from A to B to C to back to B to A and so on. And we've heard this before because we know that if we go back to our system archetypes, if we have a balancing feedback loop with delay, we're told that one of the problems with that is it can lead to oscillations. And so I could say, like, if I've got maybe my gap above B, and then I've got my movement to left. Well, if the my movement to left is going to decrease the gap that I have above B, where above is to the right of B, but then my gap above B doesn't cause movement to the left until after a delay. So I'll highlight the delay there. Then I've got this balancing feedback loop with delay. And we know that balancing feedback loops with delay lead to oscillations or ringing. So one other possibility with is that it could rise up, start oscillating, but then it could settle down to some point. And that's what we refer to as ringing. Or you can actually get growing oscillations where it doesn't actually be stable. So already add a little bit of delay in and things get ugly. Now, what we're going to start talking about, and you're going to read about on Thursday, is if now couple this delay with an uglier basin function here. It's got a bunch of little nooks and crannies, like it's got a little pop-up, like a bunch of tiny little basins and funny spaces like that. And then it becomes really difficult to predict what's going on. And what you can get is something called chaos. And so what we're going to define this week is what chaos is formally and where it comes from. And there are two major sources of chaos: delay with nonlinear feedback, or having more than three variables. So that's the other thing that we'll talk about on Thursday, is that once you've got more than three endogenous variables, it's like you can't picture a ball rolling around on a landscape anymore. It's almost like the ball has got a color, and depending on the color of the ball, you have a different landscape. But depending on the landscape, you get a different color ball. And it just totally is something that does not very conceptually helpful, this ball-in-basin stuff. And it also can emit these chaotic dynamics. And those two conditions allow you to get chaos. And that's what we'll talk about. And how do we restore some of that conceptual, or some of that predictability after we recognize the phenomenon. So that's all I've got for you today. What I'll do for the attendance slide here is how about give me a name for the point where if an exogenous variable goes beyond, it changes the number of stability regimes in a system. So give me a name. I gave you a couple of names. So one of those names that represents the point where if an exogenous variable goes past it, it changes the number or quality of the stability regimes. You can give me kind of the common name or the kind of more mathematical sounding name. And otherwise, that's all I got for you. So see you Thursday. I think you'll like the readings. They're pretty high level. They have a lot of great examples in them. So You too.